any vector with length 1 is called a unit vector. We're being asked to take vector u, 3, 2, 1, which I've sketched here, kind of pointing up from the origin. We're asked to take that vector and find a unit vector, a vector with a length of 1 that points in the same direction. So if I think about this, the magnitude of u is the square root of 9 plus 4 plus 1, or the square root of 14, which is just about 3.7. So the vector I have drawn here is about 3.7 units long. So the unit vector that points in that same direction is the vector that's 1 unit long, right? Just a little bit of the way up on that vector, right? So a little hard to see. But I have a long vector that's just under 4 units long, and there should be a unit vector pointing up along that vector that's, well, only 1 unit long. So imagine just going 1 unit out and up and away from the origin. All right, so I have to figure out a way somehow to take this vector and change its length from 3.7, or square root of 14, down to just 1. And then I remember, that's what scalar multiplication does. So I need to make my vector shorter. So I can take my vector u, and I can imagine multiplying it by 1 over root 14. Because we know the magnitude of a vector times a scalar is the absolute value of the scalar times the magnitude of the vector. So in effect, to form this unit vector, what I'm going to do is I'm going to divide the vector by its own magnitude. And so one way of writing this unit vector down is to say, well, it's u divided by its own magnitude. And anytime we write this collection of symbols, it'll let our reader know that, hey, that's a unit vector, right? U divided by its own magnitude. If I do that with any vector, it turns it into a vector with length 1. So now I need to imagine multiplying by 1 over root 14. So this vector would be 3 over root 14, comma 2 over root 14, comma 1 over root 14. So we've created a unit vector. And anytime we were to perform that process, we'd create a unit vector. In fact, this unit vector has the same direction as the vector u that I started with, and we call it the direction of u. And this actually gives us a way of writing down a vector in terms of its 2 most important properties. When we started talking about vectors, we said a vector measured a quantity with a magnitude and a direction. Well, we learned right away how to find the magnitude, and now we know how to express the direction. This is the vector u expressed as a product of its magnitude and its direction. So the vector u I started with a minute ago was 3, 2, 1, but I could also write it down as root 14 times the 3 over root 14, 2 over root 14, 1 over root 14. And there, my reader would see right away how long that vector is and in what direction it's pointing. All right. So let's talk about 3 very important unit vectors. I, j, and k. And these unit vectors are so special, I don't even draw a vector hat on top. I draw a special vector hat that means unit vector. So this would say I'm a vector. This says I'm a unit vector. The vector I is the unit vector that points 1 unit down the x-axis. Vector j points 1 unit up the y-axis, or over on the y-axis, depending on how we're thinking about it. And k, it points 1 unit up on the z-axis. And so if in my 3-dimensional coordinate system, that right-handed coordinate system, I can very easily see the vectors I j, we'll pretend I drew that right down the y-axis, and then vector k 1 unit up on the z-axis. These 3 unit vectors give us a very handy way of writing down vectors moving forward. So if I was to imagine that vector, I started this conversation off with u equals 3, 2, 1. Well, I could rewrite that in this kind of silly way. Just thinking about adding 3 very boring vectors together. Right, if I added these 2 vectors together, I would get 3, 2, 0. If I add this one to that one, I get 3, 2, 1. Well, I could then do some factoring. Now, I don't even have to really do anything for this last one. And what I see now is that this is 3 times the vector I plus 2 times the vector j plus 1 times the vector k. That the vector 3, 2, 1 is the same as 3i plus 2j plus k, giving me another way of writing down the component form of a vector. And so now we see anytime I'd have a vector a, b, c, I could write it down as ai plus b times the vector j plus c times the vector k. When we do this, it's always important to use the vector hats, let our readers know that we are talking about a vector, not a scalar, and then I see the component form. Even better than that, using this notation, if I was to take a vector and a different vector, this time I'll call that other vector w, and I wanted to add those 2 vectors. Well, I know exactly how to do that, but if I take those vectors and I write them down in our new notation, vector v would be minus I plus 2j plus 4k, and vector w would be I plus 3j minus 5k. And now if I just think about writing those 2 vectors down and adding them up, all I'm really doing is combining like terms. Right? Following the rules for vector addition, I'm supposed to add the I parts, I'm supposed to add the j parts, and I'm supposed to add the k parts, and I'm really just adding like terms, so I'd have 0 i's, 5 j's, and a minus k. Okay, so we have 2 different notations for vectors, one using vector brackets and then the ijk kind of component form for vectors. Don't mix them up, right? We're either using the brackets or we're using the ijk's, and if we're using the ijk's, we must use vector hats. I have one more thing I want to show you in this video, and it kind of takes us back to plane vectors. It's something that you might have seen in a previous math class. So let's take the vector u in the plane to be the vector 5, 5. Nothing too interesting. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's my vector u. Let's write u down in terms of its magnitude and its direction. And right away I see the length is 5 root 2. And so the vector u would be its length times a unit vector in the same direction. So I need to divide u by its magnitude. So 1 over root 2, 1 over root 2. And that's a good way of leaving it, but I recognize root 2 over 2 happening in both those places if I rationalize the denominator. And so what I realize is that any unit vector in the plane can be thought of as a spot where my vector hits my unit circle, right? That's one of those nice happy places. In fact, any spot on my unit circle can be represented with a cosine theta comma sine theta. So for this particular example, very easy, right? It's a 45-degree angle or pi quarters. But generally in the plane, I can always write a vector down as its magnitude times its direction, but expressed as a unit vector on my unit circle, where theta is that direction angle. I don't have an analogous way of saying that in the plane right now. There actually is a way of doing it that we can talk about later on.